long time ago, I did mention the distributions that we would be using in this class, starting with normal, T, F, chi-squared, and I guess that's it for this class, but there are plenty more distributions. What is a T distribution? T distribution is used in t-tests, and there are theoretical reasons for it beyond the scope of this class. So all you have to know is how to find the critical value or cutoff. We have seen how to do it using a normal distribution. We're going to extend it to a t distribution. Number two, how to find p-value. Both of those can be easily accomplished using a calculator. So if you have your TI calculator, go ahead and grab it. So critical values and probabilities can be obtained from a t distribution provided we know something called DF. DF stands for degrees of freedom. This will change depending on the scenario or depending on the nature of the test. Not every t-test is the same. So depending on the type of experiment, type of study, you'll have different tests. That said, I will tell you the degrees of freedom to use for a particular test. Same applies when you do a homework problem. Okay, if you know the DF, you can't get critical values, you can get probabilities. So we are finding critical values from a t distribution with DF equals 16 for three cases. A, some left tail test. B, a right tail test. C, a two tail test. Or confidence interval. They are related, whether you look at it as a two tail test or a confidence interval, the inference more or less is going to be the same. With TF equals 16 and use alpha, let's do 0.05, the conventional level. It is always a good idea to draw the distributions, understand how alpha relates to the cutoff value that you have, so that, you know, when we get to a test, you understand things better. So fine. Good. So first case is left-tailed. the center is 0. I believe I've mentioned this in class, or well, this is class also, but during our regular schedule, I've mentioned it before, that books tend to simply put the critical value on the line above. I like to do it separately so that we understand where the rejection region starts in a better way and keep it separate from probability. First scenario is a left tail test. The rejection region or critical region is on the left-hand side. So whatever number that we will get will be negative. So on the real number line, that is my rejection region. The area that is under the curve must correspond to what value? So the area under the curve, since we are finding critical values, data is not being used, so that should equal to alpha. So we can use our calculator. So you can press second, followed by bars. Easier way to identify the button. In blue, it says DISTR, D-I-S-T-R, short for distribution. Option number 4, inverse T. Anything that starts with INV simply means you are finding critical values. So any function that starts with INV will correspond to critical values. Area below the critical value is simply the area that I shaded, 0.05. So back to calculator, 0.05, comma, degrees of freedom. In our case, I've given degrees of freedom to be 16 in the problem. Getting a negative number, all is well. Answer is negative 1.746. The rejection region or critical region for a right tail test should be on the right-hand side. So, right side, that is my rejection region on the real number line, and area under the curve, once again, would be alpha, so 0.05. Key thing to note, inverse T in the calculator always looks for the area below or the area to the left. As I write it this way, area to the left, followed by whatever degrees of freedom. But when we do a right tail test, you have the area to the right, but if you have the area to the right, you could actually get the area to the left. So area to the right is 0.05, therefore, area to the left in this case would simply be 1 minus alpha. So when you put it in the calculator, you would actually do inverse t, 1 minus 0.05, which is alpha, comma 16. It's given in the problem, the GF. So go to the calculator one more time. Second, vars, number 4, area to the left, 0.95, comma 16 plus Bren, enter. 1.7458. Interesting. So if you observe closely, that number and that number are the same in magnitude. They differ only by sign. So you can either simply stick with the left side approach and change the sign, or take two separate approaches to get critical values like I showed you here. Last case. If you know how to find the critical value for a left tail test or a right tail test, it is easy to find critical values for a two-tailed test as well. The only difference, here is that I have two rejection regions, one on the right, one on the left, and what is the area that is shaded under the curve on either side? Think about it. So 0.05 divided by 2, that is all you need to know. The same logic applies to confidence intervals as well. So here, 0.05 over 2, 0.05 over 2. The rest is easy. We know the area to the left. We simply have to find critical value using inverse t. So back to the calculator. I'm sticking to the left. Easier. So second vars, option 4, 0.025, comma 16. Enter. Negative 2.12. Or if you want, you could have it as 19, but I can round in this case. If I know what I have on the left-hand side, the value on the right-hand side is simply 2.12 without the negative sign. Are we clear? So if you don't have inverse t, you go to the textbook, Appendix B, statistical tables, second one, t distributions. I typically put these in with the question in a test. So since we are using Responders and simply doing it online, there are advantages. We can minimize, resources. We don't have to print. I will provide you this. So they clearly specify whether to look on one side or two sides. If you draw the picture like we did, once you draw it, you simply know which option to pick from this table. So the first two cases, we had area on one side. The degrees of freedom that I provided you with was 16. So scroll down to 16 right there. And since the first two cases are left-tailed, right-tailed, we are looking at the area of 0.05. Scroll down, it's right over there, 1.746. That's the answer we had. The next case was two-tailed. The area under the curve on either side or either tail is 0.025, but the combined area is still 0.05. You're adding whatever area that you have on the left-hand side with the area on the right-hand side. So you look at the last three columns and scroll down, and it's right over there, 2.12. That is exactly the answer we had obtained earlier using the calculator. So 2.12 and 1.746. If you recall from our previous lectures, every hypothesis test requires a test statistic computed using the sample or the data. It is a formula of sorts. So some formulas are easy, some are pretty complicated. So I'm going to consider a single sample t-test. A single sample t-test is used to test hypotheses about the mean. Oops. Notice I'm putting mu. Mu is the population mean. So the test statistic here is t equal to x bar minus mu divided by s over square root of n. That is the formula. So mu is the population mean. X bar, sample mean. S, sample standard deviation. Lastly, n, sample size. So if you don't have a test statistic, you cannot conclude a hypothesis about the population parameter, in this case, mu, the population mean. So we need to find this. From one of our previous lectures, this was one of the steps in hypothesis testing. So as an example, let's say suppose a right tail test single sample for mean. I'll even specify that it is a t-test. Is performed for some hypothesis. Using the data we have x bar to be 13.21. Standard deviation is 2.4. The number of observations or sample size is 8. So someone did a test and they collected a sample with 8 observations. Using those observations, they found the mean, they found the standard deviation, which are 13.21 and 2.4 respectively. Now, our goal is, should we reject or not reject the null? Let's even give a definition to avoid confusion. Let's say mu is less than or equal to 14. Alternative, mu greater than 14, specifically picking greater than because I stated in the problem that this is a right tail test. So we need to obtain a conclusion as to whether we are going to reject the null or not reject the null. So for the test at hand, we have data, we computed statistics from the data, we have the mean, we have the standard deviation, sample size. So put them all together, I can come up with the test statistic, and that will help us come up with a solution. Algebra. Finally, math. So t x bar minus mu over s over square root of n. We know what x bar is, 13.21. We know what mu is, 14. Divided by s, 2.4. N, 8, therefore square root of 8. When you put it in the calculator, make sure you use parentheses. Don't type it directly without parentheses. You will get the wrong answer. So 0.79 divided by 2.4. Approximately, I'm thinking perhaps about 0.86. You have the calculator, so divide this to should be about 0.86. Or is it? No, take that back. Less than that. If you look at what I wrote, I forgot the square root of 8. Now it should be about 0.86 or so. Parentheses are important. The numerator is 0.79. Denominator 2.4 over square root of 8. Second, x squared 8. 0.92. I underestimated. Okay. So approximately 0.93. So we have a test statistic. Now we want to attain a conclusion. Going back to what we did earlier, we know how to find critical values. If I identify the correct critical value, then I know the rejection region. Then I ask myself the question whether 0.93 will fall in the rejection region or not. Very good, Luana. Why is it not negative? It has to be negative. I did bad algebra. Negative for sure. So based on what we learned earlier, let's see if you can find the critical value and come to a conclusion. Should you reject the null or should you not reject the null? I strongly recommend that you draw the distribution, draw the rejection region until you get comfortable. That is key. You won't be making mistakes if you draw this. So I'm going to draw the distribution. Going to use an alpha of 0.05. The problem will clearly state as to what the value of alpha should be. So alpha is 0.05, right tail test. So the area should be on the right-hand side. On the real number line, that is the rejection region. I don't even have to use a calculator. I know for a fact the test statistic is not going to fall in the rejection region. But we can use the calculator to find the critical value, so we have no practice. Can someone tell me why I know the conclusion already? Think logically. It'll be given in the problem. Olivia. Very good, Riley, because t is negative. So the test statistic that we computed is negative. So it clearly is not going to fall in the rejection region that I have. But for practice, let's go ahead and find the critical value. So inverse t alpha 0.25. The degrees of freedom in this case is 7. Now, don't get confused here. I know for this problem, the degrees of freedom is 1 less than the sample size. Luana was able to come to a conclusion. Riley was able to come to a conclusion directly because it's obvious. I intentionally made it obvious, but as a side note, for a single sample t-test, df is n-1. Earlier, I mentioned that depending on the test, the formula for df will change. So for a single sample t-test, the df is n-1. So we put it in the calculator, we ended up guessing 1.89. That would be that number. Well, my test statistic is way over here. Obviously, it is not going to fall in the rejection region. Do keep in mind, some like to call it the t-value, some like to call it t-score. I say tomato, you say tomato, we're all talking about the same thing. So don't forget that. So since test statistic doesn't fall in the rejection region, we can conclude that the null should not be rejected. Is there statistical significance? Yes or no? In order to conclude that there is statistical significance, one must reject the null. If you don't reject the null, there is no statistical significance. Is it necessary to assess practical significance in this case, in this example, i.e., computing effect size? Is it necessary? Very good. This time you're making me proud. The answer is no. Had I found statistical significance, I would go and assess if it is also practically significant. But If there is no statistical significance, we just stop right there. Because I do it too. Suppose the null is rejected. So this statement indicates that we need to assess for practical significance. Hence, I'm going to compute effect size. I'm giving you mean, population mean, standard deviation. I'm computing the effect size using the formula, which would also be given. I get a value of negative 0.5. If you recall, the Cohen's d levels maybe it's 0.2, 0.5, 0.8, and we end up calling the size to be small, large, medium, large. So here we have -5, but when we use the table, we look at the absolute value. So it is 0.5. So absolute value of D. Let me put that here this way. You don't confuse yourself. Absolute value of D. So in our case, the effect size is median. So if you look at the formula for Cohen's d, I have it as x bar minus mu over s. If you look at the formula for a one sample t-test, which is right there, I have x bar minus mu divided by s over square root of n. Cohen's d, which is the effect size. Here, it is the test statistic. What is the difference that we observe? Aside from one's called D and the other T, there is a difference in the formula. Very good. So if you observe effect size, it does not depend on sample size. Test statistic depends on sample size. So if sample size increases, in other words, we conducted a new study with a larger sample size. The effect size might end up being the same. But we will be more likely to reject null because t will become larger. This is just a side note, but what I'm trying to say here is if you keep on changing the sample size, you would simply conclude that, oh, I'm rejecting the no. But the true effect may not change. For all I know, it might just stay at median. So you will simply conclude that there is statistical significance because you are increasing the sample size. T is probably getting larger and larger and larger in magnitude, but D doesn't change. This is what I refer to as, p-value hacking or things that you shouldn't do in statistics. This is the reason why we simply don't go with statistical significance. If we find statistical significance, we should assess for practical significance, because effect size or practical significance does not depend on the sample size. So key difference. One last thing, S by itself is standard deviation. However, the denominator here is standard error. They are not the same. This is not a theory-based class, so I won't get into too much detail, but S is the standard deviation. S over square root of n is called the standard error. So know the difference.